Hello, listeners. This is Mike, your host. If you are enjoying these archive episodes, please consider supporting the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange donate button or the Patreon link. Hopefully, with your support, I can continue to release these archive episodes. Thanks.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Listen, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 137 of the Space Rocket History Podcast. And now, Apollo 1, Changes and Recovery.
Since the accident, 1 million words were spoken and 1 million words were written. Not all of them competent. We know that we have taken on a very challenging program, or as Bill Allen, the president of Boeing, said that night, this reminds one again that we are not in the business of making shoes. It is our job as engineers to make sure that these risks that are unavoidable are reduced to the bare minimum. 3 brave men lost their lives for space flight, and I think we owe it to Gus Grissom, to Ed White, and to Roger Chaffee that we go back and put our program back into gear where it belongs.
And we had a NASA committee that looked at what was wrong, and everything was wrong. It was poor workmanship, poor wiring, poor redundancy concepts, etc. And so we had a regrouping of NASA following Mr. Thompson's review of that program. And one of the first meetings we had with George Lowe as the new program manager was a meeting to decide what we needed to do. And we listed 125 things that had to be done to make that spacecraft viable. And we did that. We worked our fannies off, and we got it done, along with the many contractors in this country. And in 1967, after having done that and getting ourselves ready to go, it took a lot of guts, frankly. We had to rebuild the industry, had to rebuild ourselves, and we had to rebuild the spacecraft.
The familiar voices of Wernher von Braun and flight director Chris Kraft. Immediately after the fire, NASA realized that what happened to the command module obviously could just as well happen to the lunar module. So, Thomas Kelly and a host of Grumman workers began a comprehensive review of materials in the lunar lander. George Lowe sent Robert Johnston, who was a materials expert, to help Kelly's group. Grumman replaced nylon cloth in the spacecraft with beta fiber. Now, beta fiber is an inorganic substance developed by the Corning Glass Works that would not catch fire nor produce toxic fumes. Perhaps the most important application of this material was as booties around the circuit breakers to lessen the possibilities of electrical shorts. In other areas, Grumman worked on its forward hatch to ensure a crew could exit within 10 seconds. They also made changes to the environmental control system and added a cabin and exterior pressure equalization system. All in all, the changes would add 3 to 4 months delay in delivery of the lunar module that was already behind schedule even before the fire. Also, a group headed by Roderick Middleton of Kennedy was sent to look into Grumman's quality control and inspection procedures. Middleton's audit team completed its work in mid-May, giving Grumman generally good marks in the manufacturing process. Now back to the command module. After the uncertain days of February, NASA officials began to realize that a recovery from the tragedy was underway. Through hard work and problem solving, morale of NASA personnel started to improve. NASA was very aware that much of Apollo's chance for recovery rested on the fact that the Block 2 advanced version of the command module was well along in manufacturing and that most of its features were direct improvements over the faults of the Earth Orbital Block 1 version. Moreover, the Saturn V, after experiencing difficulties in the development of its stages, seemed to be on track now. Within days after the Thompson Board report, more than 1,000 employees at the Manned Spacecraft Center who were working directly supporting the formal investigation began making suggestions for meeting the board's recommendations. In Houston, Max Faget's engineering and development team ran all sorts of tests on materials and components, material selection, substitution, and stowage inside the command module were thoroughly restudied, and all cloth parts made of nylon were replaced by beta fiber, Teflon, or fiberglass. These substitutes were chosen after more than 3,000 laboratory tests had been run on more than 500 different kinds of material. Robert Gilruth sent Frank Borman with a Houston Tiger team to North American in mid-April. Borman was to make on-the-spot decisions on contractual changes for the unified hatch, better wiring and plumbing techniques, and other improvements that had been planned even before the accident. Borman's Tiger team watched closely, lending its assistance when necessary as North American engineers went over the spacecraft piece by piece. Of immediate importance, of course, was the new unified hatch. Unified meaning that the complicated two-hatch system was redesigned into a single hatch. The hatch had a manual release for either internal or external operation, and it would force the boost cover cap out of the way on opening. The new hatch was heavier than the old, but it could be opened outward in 7 seconds by the crew inside the capsule, and a pad safety crew outside the capsule could open it in 10 seconds. It would also be designed to open independent of internal overpressure and would be protected against accidental opening by a mechanism and a seal similar to those used on Gemini. Ease of opening was enhanced by a gas-powered counterbalance mechanism. The second major modification was the change in the launch pad spacecraft cabin atmosphere for pre-launch testing. The atmosphere was changed from 100% oxygen to a mixture of 60% oxygen and 40% nitrogen to reduce support of any combustion. The crew's suit still carried 100% oxygen. After launch, the 60-40 mix was gradually replaced with pure oxygen until the cabin atmosphere reached 100% oxygen, but at only 5 pounds per square inch. This enriched air mix was selected after extensive flammability tests in various percentages of oxygen at different pressure levels. Other modifications included substituting stainless steel for aluminum in high-pressure oxygen tubing. Solder joints on the water glycol liquid line were armor-plated. Protective covers were installed over wiring bundles. Stowage boxes were now made of aluminum. Flammable materials were replaced. Mechanical fasteners substituted for gripper cloth patches. Wire connections were coated in flame-proof material. Plastic switches were replaced with metal ones. An emergency oxygen system was installed to isolate the crew from toxic fumes. Portable fire extinguishers were added, and fire isolating panels were installed in the cabin. Safety changes were also made at Launch Complex 34. These included structural changes to the White Room for the new quick-opening spacecraft hatch, improved firefighting equipment, improved emergency egress routes, improved emergency access to the spacecraft. All electrical equipment in the White Room was purged with nitrogen. A handheld water hose and a large exhaust fan in the White Room were added to draw smoke and fumes out. The White Room was covered with fire-resistant paint. A water spray system was added to cool the launch escape system. This is due to the fact that solid propellants on the launch escape system could be ignited by extreme heat. A sliding wire was added to the service structure to permit a rapid descent to the ground. Additional water spray systems were added along the egress route from the spacecraft to ground level, and personal emergency preparations were emphasized as never before. The management of all industrial safety offices within NASA was revamped as well, with responsibilities flowing directly to the top at each location. Reliability and test procedures were more firmly controlled, making it difficult to inject any last-minute or unnecessary changes. At NASA headquarters, Administrator Webb directed Miller to revamp and reorganize the major supporting and integrating contractors to put more pressure on North American, as well as on those manufacturing the other Apollo vehicles. Boeing was given a technical integration and evaluation contract to act as a watchdog for NASA, and General Electric was told to assume a much greater role in system analysis and ground support. While these changes were being put in place, hearings were still being conducted. North American was given the opportunity to inform Congress on the changes they were making. North American's Leland Atwood and Dale Myers used charts to emphasize the changes that the company intended to make in both construction and test operations. North American would now assign a spacecraft manager and a personalized team to each vehicle, and appoint an assistant program manager whose only concern was safety. North American would place additional controls on design changes made during modification and checkout phases, and assign personal responsibility to specific inspectors. The company would also revise its fabrication and inspection criteria, expand its quality standards, issue a handbook with better visual aids, install more protective wiring and plumbing, and insist upon additional major inspections. Dale Myers then discussed fire-related hardware changes, such as the unified hatch, materials reevaluation, fluids and plumbing reassessment, electrical system improvements, revised on-the-pad operations, and flammability test. Now, a word about the business relationship between North American and NASA. North American's contract had expired in December of 1966, and after the fire there was some consideration of moving away from North American. But at this stage of Apollo, that was clearly not practical. So, despite the fire, John J. McClintock, chief of the Apollo Office Programs Control Division, advocated in April 1967 that NASA negotiate a follow-on incentive contract with North American, placing heaviest emphasis on flight performance and quality and less on schedules. North American's business negotiators had already conceded that no incentive fee could be expected for the Apollo 1 spacecraft. The closeout cost for the Block 1 series of Apollo was now set at $37.4 million. This meant that the learning phase of Apollo had a total cost of $616 million. Furthermore, North American agreed that there would be no charge for changes resulting from the Apollo 1 accident, such as the wiring harnesses, environmental control system improvements, and the unified hatch. But changes that would enhance mission success or operational flexibility, such as changes in the reaction control system, the revised inspection criteria, and features to increase mission longevity, would require additional money. Okay, moving past the North American issues. At the time of the accident, the flight schedule had listed a possible lunar landing before the end of 1968. But after the impounding of material evidence and the halting of oxygen chamber testing until the investigation was over, that Apollo schedule was obviously no longer valid. So, several weeks after the fire, Siemens told Miller to scrap all official flight schedules for manned Apollo mission and use only an internal working schedule to prevent avoidable slips and cost overruns. By March, Miller had told Siemens that NASA could commit a Saturn V to a mission. In June, Lowe said he believed that the spacecraft had turned the corner toward recovery, since the changes related to the fire had been identified and were being made. But even if everything went perfectly, more than 14 months would be needed for a complete recovery. To make certain of stronger program control in the future, Lowe decided that all proposals for changes would have to pass an exceedingly tough configuration control board before being adopted. He asked his assistant, George Abey, to draft a strongly worded charter for the control board. Lowe next announced that he, Max Faget, Chris Kraft, Deke Slayton, Kenneth Kleinnick, William Lee, Thomas Markley, and Abby as secretary would meet for several hours every Friday, and when medical and scientific affairs were on the agenda, Barry and Wilmot Hess would join the group. Lowe himself would make all final decisions on changes, and his new board members had the authority to ensure that his decisions were carried out. Now, if Apollo had seemed complicated before the fire, it appeared even more so afterward. If it gave an impression of being hurried in late 1966, it gathered still more momentum in late 1967. If an extreme level of attention had been given to aspects of crew safety and mission success before the deaths of the crew, it now rose yet higher after they were gone. But among the Apollo managers, there were still nagging fears that something might slip past them. Something might be impossible to solve. By mid-1967, however, they were so deep in their work that they could not avoid a growing confidence. Back at North American, things were improving as well. Bergen, Harrison Storm's replacement, was making his presence known. Bergen actually moved into the factory while recovery work was going on. He made a practice of appearing on the plant floor, walking around, asking questions, during each of the 3 shifts. Some of the workers wondered if Bergen ever slept. During visits to Downey, George Low was often seen watching plant activities on Saturdays. This, along with Frank Borman's Tiger Team and Healy's performance as manager of Spacecraft 101, were key to getting the command module back into line. NASA leaders, after reviewing the progress, decided that it was time for a flight demonstration to prove that the bits and pieces of Apollo had been picked up and were being put back together. Apollo Saturn Mission 501 with Command Module 17 was set for early autumn of 1967. If the first flight of the Apollo-Saturn V combination was successful, the rest should follow in due course. But as early as May 9, 1967, Houston proposed 4 manned missions, one with only the command and service modules, the other 3 with all vehicles. These would all be non-lunar landing missions. Headquarters in Washington believed that the lunar landing mission might be possible on the 4th manned flight, but Houston thought that was unrealistic. Chris Kraft warned Low that a lunar landing should not be attempted on the first flight, which leaves the Earth's gravitational field. There was still much to be gained from the operations which could be conducted on the way to and in the vicinity of the Moon. The many questions of thermal control away from the Earth's environment, navigation and control during translunar flight, communications and tracking at lunar distances, lighting conditions and other flight experiences affecting astronaut activities in the vicinity of the Moon, lunar orbit and rendezvous techniques, and many other operating problems could be revealed with a non-landing lunar flight. In June of 1967, Deputy Administrator Siemens and his aides made a swing around the manned spaceflight circuit, visiting Kennedy, Huntsville, Mississippi Test, Machoud, and Houston. In the course of the tour, Siemens observed a definite upsurge of confidence within the Apollo team, although there still were worries. For example, at Kennedy, with planning predicated on a 6-week checkout of the Apollo Saturn in the Cape facilities and launch during the 7th week, there was some feeling that the schedule for the launch of Apollo 4, an unmanned Saturn V flight, was extremely tight. Huntsville was still worried about the S2 stage of the launch vehicle, which had gone through a rather tough year of testing in 1966. And Houston, as a result of fire-related changes, was fighting the age-old problem of increased weight of the craft. On top of this, the lunar module was still having ascent engine instability problems, also left over from the preceding year. The next month, in July, Miller and an entourage visited the North American plant at Downey to see what the contractor had done about the Thompson Board's recommendations. As they walked around the manufacturing area, Miller seemed generally pleased with progress, and within a few months, that progress was to be demonstrated in a very satisfactory manner. As we close out the topic of Apollo 1, I thought it would be appropriate to read a crew eulogy written by Mary C. White. The fire which claimed the lives of Gus Grissom, Ed White, and Roger Chaffee stunned the nation and rocked the National Aeronautics and Space Administration. The disaster had the potential to bring a permanent halt to American efforts in space exploration. Rather than bury its head in the sand, NASA launched a full-scale investigation of the fire and voluntarily put the entire Apollo program, including its administration, policies and procedures under the scrutiny of a review board. Based on the board's findings, NASA rolled up its sleeves and went to work to resolve the problems that had been identified. A successful failure is a mission which fails to reach its objectives and yet still achieves an element of success. Apollo 1 never left the launch pad. However, the information gained from this fatal mission paved the way for a redesigned Apollo spacecraft, 11 Apollo spaceflights, and 6 lunar landings. Although Grissom, White, and Chaffee never walked on the moon, their sacrifice helped to make it possible for us to collectively take one giant leap for mankind. It is crucial to remember the hard lessons learned from Apollo 1, and eulogies are part of that remembering. Yet Grissom, White, and Chaffee may be honored best by continuing the work they began. Each of them believed that reaching the moon was not meant to be an end, but a beginning. 50 years ago, Grissom considered manned missions to Mars and crews assembling, living, and working on space stations as realistic follow-ups to a lunar landing. While he recognized the place of ever-improving technology, White was emphatic about the need for manned missions. He said, quote, "You'll never satisfy man's curiosity unless a man goes himself," end quote. Only weeks before he died, Gus Grissom wrote the following: "There will be risk, as there are in any experimental program, and sooner or later we're going to run head-on into the law of averages and lose somebody. I hope this never happens, and perhaps it never will, but if it does, I hope the American people won't think it too high a price to pay for our space program." We can honor Grissom, White, and Chaffee only if we follow in their footsteps and peacefully continue to explore space. Our future work in space is bound to include other successful failures, yet Apollo 1 has taught us that we can never really fail as long as we doggedly persist in our efforts. The greatest lesson we can learn from Grissom, White, and Chaffee is that failure is impossible for those who refuse to abandon their goals. Ultimately, the most fitting tribute to the crew of Apollo 1 is for us to continue doing that for which they gave their lives. As we expand our boundaries further into space, beyond this tiny sphere into the vast universe, we honor Gus Grissom, Ed White, and Roger Chaffee. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange donate button or the Patreon link. Thanks.